I'm very pleased to be able to introduce our first speaker, Professor Michel Mandjes. Professor Mandjes is the project lead of Networks, a 10-year program funded by the Dutch Ministry of Education, Culture and Science. He has been a full professor at the University of Amsterdam since 2006 and previously was at Bell Labs, the University of Twente, and a department head at CWI in Amsterdam. His research interests include stochastic processes, queuing systems, efficient simulation techniques, and their applications. He has published over 200 journal and conference papers, supervised over 30 PhDs to completion, serves on the editorial board of 5 journals, and has a large number of active collaborations with international partners. With this background, Professor Mandjes is an ideal speaker to set the scene for this workshop. He is going to give his perspective on the area of data-driven queuing by identifying 5 branches of work and illustrating each with some selected papers. So it's over to you, Michel.
Well, thanks a lot for this introduction, Nikki. So it's of course a great pleasure to speak at this multi-continent workshop. It's a very interesting experiment, and I'm very curious how everything will pan out. Also very curious to the contributions of all the other speakers. Okay, so Nikki already said it. I'll give my own perspective on this area of data-driven queuing challenges. And let me start with a statement. That statement is that, in my opinion, data has always played a role in stochastic operations research. And to substantiate that claim, let me first tell you what I think stochastic operations research is. Well, that is the area of complex systems that operate under randomness and uncertainty, and that aims to develop mathematical models and techniques. And why do we do that? Well, we want to analyze and optimize those systems. And what kind of systems do we have in mind? Well, that can be systems from transport, logistics, it can be healthcare systems, it can be systems from engineering, etc. Well, then what I think is let's say the traditional approach that people have followed so far in stochastic operations research, and that is the following approach. In the first place, I think there is always this first stage in which the model is estimated in a sort of external loop, and quite often that's done by relying on statistical techniques. And then given a model, you want to evaluate the performance of that model, and that model can be a queue or an inventory system or something along those lines. And that is often done using, well, probability theory, so like queuing theory, for instance. And then there is typically a design phase, and quite often there's something to optimize, and then you can rely on techniques from optimization theory. So there's this triple, starting with statistics, performance evaluation, optimization, design, that kind of thing. And to illustrate that, have a look at this example, appointment scheduling in healthcare. So there are clients who seek service from a doctor. Well, they need specific treatments. And basically you want to optimize an objective function that takes into account the waiting times of the patients and the idle times of the doctors. And it's not hard to see that, well, a generous scheme is good for, having no waiting times, but quite substantial idle times, and vice versa. If you go for a tight scheme, that's the other way around. So you want to find sort of the optimal trade-off here. So what would be this traditional conventional OR approach that you could follow here? Well, you use statistical techniques to estimate, well, the treatment time distributions that you do typically through historical data. So that can be like a log normal distribution for the treatment of a certain type, coefficient of variation typically below 1. This is just an example, of course. And then you can use queuing theory to, well, devise a procedure to evaluate the objective function, remember in terms of the waiting times and idle times, and that is for given appointment times and for a given sequence of the patients. And then you can use optimization techniques to minimize the objective function, and that gives you like the optimal schedule. So you see statistics, queuing in this case, and optimization as the 3 steps that you go through. Well, I think a very legitimate question at this point is this the way that we should do this in 2021? And I think my answer is no, and that is no for various reasons. Just a few considerations from my side. In the first place, I think one flaw of this approach is that we take the parameter values for granted. Of course, there is like uncertainty in the parameter estimation, and that should be brought into the equation. In the second place, and I think that's almost always neglected, the schedule changes the system. So the doctor tends to work faster when she's behind of schedule, or slower when she's ahead of schedule. So there is this interesting interaction between, well, the current state of the system and the service speed. The question arises, shouldn't we simultaneously estimate and optimize? In the third place, I would say, is this the way that we would like to organize a booking system? Shouldn't there be like an app with an interface that enables patients to book the slot themselves? I think that is the way we should go about it nowadays. And the other thing is, when you're behind of schedule, wouldn't we want to notify the patient about that, right? That's, well, sort of creates less annoyance with the patients, and that's exactly what you would like to achieve. So there are all kinds of things that we would do differently, and I think that is the trigger for, well, thinking about these problems in a different manner. So this talk is, as Nikki announced, very much about my own perspective on things. Of course, very much colored by the projects that I was involved in. I'll give this view, but first I should include a big disclaimer, actually, because, well, there is this book, The World According to Garp. Well, this is really the world according to Michel. I'm giving my own perspective, and I can very well imagine that your view on these things is a bit different depending on, well, your own perspectives and your own position. It's very important to realize that the field is extremely broad and also not so uniquely defined. What are data-driven queuing challenges? The other thing is that I'm not going to give you a sort of exhaustive overview, so I'm not covering all the material in this field. And I follow very much my personal taste, and I'll give like a few pointers to, well, particular papers that inspired me along the way, and have like crisp, interesting messages. I'll be emphasizing branches in which I'm involved myself. You will notice that. Okay, so before really starting, let me say a few things about what I see are the, let's say, the big trends that play a role when thinking about data-driven queuing challenges. Some of them are sort of obvious, other ones are a bit more, more specialized. But let me go through them. First one is a very obvious one, that is about the availability of data. If you compare our situation nowadays with what it used to be like 40 years ago, it's clear that we have access to, well, way more data, and we should do something with it. In the second place, of course, there's much more computational power, and we can exploit that. And of course, in adjacent fields, there is a lot going on. So there is this machine learning field, and in artificial intelligence, a lot is going on. Well, these are fields that I would call, and I don't mean that in a bad way, actually in a very positive way, pragmatic data analysis. And I think we can learn a lot from them, and hopefully we can interact with them and create, well, synergy from that. One thing I was already alluding to in one of the previous slides is that there are also like technological ways to, well, to work with other utility functions. What I mean to say here is that there are like these improved interfaces to interact with clients. So you can tell a client that, well, the service will start later, for instance. So that creates new problems and, well, new interesting research challenges, I think. And the last trend that I want to notice in this respect is that there is an increased awareness that we shouldn't split, right? So we had these traditional phases of estimation, performance analysis, optimization, and I guess the trend is that we should, well, merge these phases. So we shouldn't separate estimation, performance analysis, and optimization as we used to do. So there is this concept of earning and learning. I'm going to go back to that in a bit. And well, there's this idea of exploration, exploitation. So these are examples of this new paradigm. Okay, so what I did before this lecture was that I asked myself, how can I sort of divide the work going on in data-driven queuing in terms of number of subfields? And in the end, I got to 5 branches. And I believe most of the research is in one of those 5 branches, but they are, of course, overlapping in many ways. First one being in a bit traditional one, but that is about, well, let's say in-depth data studies that improve our understanding of, well, the models that we are using. A very prominent question there is, well, about the Poisson arrival assumption that we quite often make. Is that, well, a realistic assumption, or should we go for something more general, advanced, sophisticated, etc.? The second subfield is about, well, basically the question of estimating the input of a queuing system from observations from that queue. So quite often you want to know about the input, but you don't have access to the input traffic, and you want to learn it from observations of the queue. Related to that topic is the question of, well, you observe the queue and you want to know whether there was some change in the input at some point. So that's a change point problem that is also extremely relevant, I think. In the third place, there are techniques dealing with parameter uncertainty. So that is very much about, well, the theme of robust queuing, how to take into account the uncertainty of the parameter. Then there are techniques that focus on jointly estimating and optimizing queuing systems. So that is that earning and learning principle that I was already mentioning. BANDITs play a role here. And in the fifth place, there is, well, the theme around queuing models in which the service strategy depends on observations of the congestion level of the queue. And you can think of the doctor working faster when lagging behind, or you can think of, well, the TCP protocol that underlies the internet, or load balancing techniques in a way that's somehow close to sort of traditional queuing. But of course, there is the element of, well, measuring the congestion state of your network. So my impression was that these 5 branches cover, well, virtually all research that is going on in this area. And you will notice that, well, the talks that will be given in this workshop, well, fall under this umbrella, I think. And my plan for the rest of the talk is to say a bit more about each of them. So I go through all 5 of them and give my own personal perspective on what I like about it and what interesting challenges there are in the relation with more classical queuing theory. So let me start with the first one, and that is about, well, these in-depth data studies that challenge, well, the usual assumptions, such as the Poisson assumption. So quite often it's about, well, a system from reality, and, well, there's a lot of data available, and you want to challenge the conventional modeling paradigms. So let me start with an example that I came across like maybe 6 years ago or so, or a bit longer. And that's about the phenomenon of over-dispersion in the queuing system. So this is the paper that I saw at that point, a paper by Xiaowei Zhang and 2 co-authors from Hong Kong. And he's looking at a call center, and he's wondering, what can we say about the arrival stream of clients there? Well, basically, the observation of these 3 people was that those arrivals are actually more variable than would be predicted by a Poisson process. And that is that phenomenon of over-dispersion, there is more variability going on. The consequence is that, well, you have to adapt your staffing rules. The staffing rules that are typically used under the Poisson assumption are too optimistic, and you have to correct for that. So quite a bit of interesting research has been performed on that theme. So papers by Ward Witts, but also by Avi Mandelbaum and co-authors. And well, those are great reads to get a feel for what is going on. Let me say a few more words in a slightly more precise manner. So what is the underlying idea of overdispersion? Well, basically the idea, at least in my point of view, is that actually there's another cause of randomness. There are like external events that increase the variability of the arrival stream. So the Poisson arrival rate may fluctuate over time. And that gave rise to a very interesting cross-fertilization with queuing theory, because people start to think about queuing systems fed by Poisson processes with time-varying rates. And those are often called Cox processes. So there is research in that field, and basically one of the conclusions was that the usual square root staffing rule that people have been working with could be adapted. And of course, the square root that we used to have becomes something else now, rho to the power gamma, and gamma is typically bigger than a half in order to take care of the additional impacts of the random arrival rates. So this is, I think, a very good example of a data study that led to interesting new queuing theory. A second one that I enjoyed extremely when I read it is this paper by Moore Harmony and co-authors. Basically, what they do is that they look at hospital data. And when I say hospital data, I mean a huge data set. And what they do is that they, well, model the patient flow through a hospital. Well, have a look at the paper. There's a lot of interesting stuff in it. I think the most important conclusion is that you come across various features that could not explain by existing models. So really there is a very well, interesting spin-off of this study in terms of, well, interesting queuing problems to have a look at. A paper that I was involved in myself is this one. It's about aggregates of, well, a lot of traffic streams in the backbone of the internet. Well, lots of users are using that backbone simultaneously. And you may wonder what happens to the stochastic properties of this traffic aggregates. And one of the things that I expected at that point was that that should look extremely Gaussian because of, let's say, CLT type of arguments. And that turned out to be correct. So if there is enough aggregation, and that already starts at a pretty low level of aggregation, traffic in the internet is approximately Gaussian. And that's a wonderful conclusion, of course, because the Gaussian distribution is characterized by just the mean and the variance. So the only things you have to take care of is the mean and the variance. The mean is something like, well, something easy to measure. The variance is encoded in, I should say, a variance function that depends on time because, well, the length of the window has impact on the variance. So the V of t, you can see as the variance of, well, traffic generated in a window of length t. And, well, a typical form for this variance curve could be t to the power alpha. Alpha as 1 is the usual, like, Brownian type of traffic. And if alpha is bigger than 1, you end up with, well, traffic that is actually long-range dependent, and that is actually observed in the internet. So I think a typical value for alpha in the internet is 1.4 or so. I'll get back to this example later on. So this Gaussian traffic example, there's much more to say about that. So some conclusions regarding these in-depth data studies. In the first place, well, these data studies quite often reveal an anticipated phenomena and also mechanisms. And, well, the good thing for us queuing theorists is that, well, there are, well, new models are needed to describe these, and that is important. So there are all kinds of challenging new queuing theoretic questions. I try to give you a few examples, and I think there is a lot to be done there. Okay, so this was my first research branch, the big data studies. Let me move on to the second one, and that is about the problem that I mentioned to you of observing a queuing system and using those observations to estimate the input of the queue system. So we want to go for, well, a statistical description of the model primitive based on observations of maybe your workload process. So, well, this is the question that we want to resolve. The example that you could have in mind is the following. So you want to estimate the arrival rate of, let's say, an MG1 queue based on, or in the service time distribution based on workload observations of this MG1 queue. So we're in the context of an MG1 queue, and you want to use workload observations to estimate these things. Why do you want to do that? Well, quite often in practice, well, the input process is hard or impossible to measure. And if you want to estimate it, well, you run into problems. There's the second issue of estimating the load of non-joining clients. I'll say a bit more about it in a bit. A related question that is also very relevant is the, well, let's say the twin question. So you observe a queuing system and you want to know at what point the input has changed. So you want to detect a change in the input process by observing the queue. If you want to know more about this topic, then, well, have a look at this survey. So it appeared recently in queuing systems. I think it tells you everything you want to know about, well, inverse problems, but way more, actually way more. And Assam Asanjarani is going to talk about it on, yeah, I'm not sure whether I should say Wednesday or Thursday. For her, I think it's Wednesday, and for me it's Thursday or so. I don't know. No, for her it's Thursday too, but for people in the US it's actually Wednesday. Anyway, so that's the whole problem of this multi-continent workshop. Anyway, have a look at this paper. I'll give a few examples now of, well, appealing inversion problems in queuing. So the first one relates to that Gaussian example that I gave a moment ago. So what is the context? I have a resource, a queue, that is fed by a Gaussian process. And let's say that it's a stationary Gaussian process, and let me call the input process A of t, meaning that A of t is the amount of traffic that arrives in a window of width t. Well, in this context, well, there is something like the mean and variance. I was already talking about that. The mean, well, because everything is stationary, is, well, described or uniquely defined by the mean of A1. And the variance is this variance curve that I denote by V of t as before. Well, in this modeling context, there is an approximation for the stationary queue length in terms of the variational problem. And that is given by this relation. So the workload is very well approximated by this supremum. And here, of course, you recognize the exponent of the normal density. So this relation can be made formal in the large deviation sense. I'm not going to say more about it, but it's a good approximation. Interestingly, the t that optimizes the right-hand side can be interpreted as the most likely timescale of overflow. Okay, so keep this relation in mind. So we know how to compute for a given threshold u, the probability of exceeding that threshold, once we know the v of t. So this is the relation I put on the previous slides. And if you play a bit with it, then you will notice that it implies that for all u and t, there is this inequality, right? So this supremum is translated in this inequality. So that applies for all u and all t. It also means that we can swap the roles of the log probability and the v of t here. And then we get this relation. The v of t is smaller than the right-hand side here for all u and t. And then we can work our way back, meaning, basically under some regularity condition that, well, this well, there is some correspondence to the optimal t and the optimal u here, that the v of t can be written in this form. And that is extremely interesting because what we have done now is a true inversion formula. So we plug in the workload distribution, and what we get out is the variance curve. And that gives rise to well, really an inversion formula. What we can do is that we observe in measurements the workload distribution, we estimate the workload distribution, and then we perform this minimization problem, and that gives you the v of t. For all values of t, we have to evaluate another information here, but you can do that obviously, and it gives you for all timescales the v of t. And that is extremely useful because you can get estimations of v of t at all timescales simultaneously based on the same data sets, including the very short timescales that are often very relevant for dimensioning purposes, on which the a of t is hard to measure. So you can go for instance, estimation of a of t at a timescale of 1 millisecond, a very fine timescale, relying on observations of the queuing process at a timescale of perhaps every second or so. So this sounds a bit weird at first sight, that you can estimate something on a finer timescale than your observations, but actually you can, right? So that is shown here, as long as you are in the setting of these Gaussian queues. So we like this idea very much. You can sort of bootstrap your way up to, well, very nice estimates of, well, fine timescales while observing the system only at more, less fine timescales. If you want to know more about this phenomenon, have a look at this paper that I wrote with my former student Remco van der Meent about 15 years ago. Well, together with Martin Zubeldia, we revitalized this topic. So it turned out that way more could be done, and he's going to talk about it later today, meaning tomorrow for the people in Down Under. Well, this study I wanted to mention as well, inversion for the MG1 queue. Well, a study that I like very much by Hansen and Pitts. The emphasis is very much on constructing formal estimators for the arrival rate, the service time distribution, and proving properties such as consistency, asymptotic normality. In their framework, the measurements were equidistant in time. Interestingly, if you relax that a bit and you go for, well, measurements at Poisson epochs, you can do much more, as it turned out. Because in the MG1 context, you have explicit formulas for, well, the transform at Poisson epochs. And that can be exploited to set up a method of moments about which you can also prove, let's say, the consistency in the asymptotic normality. So there you need to apply the martingale CLT, but everything works out very smoothly. If you want to read more about it, then have a look at this Bernoulli paper that I wrote together with Liron Raffner and Onno Boxma. So now that I'm talking about Liron, I think there are two more papers with Liron that I would love to mention as well. The first one being this one. It's about estimating non-observable loads. Well, that sounds already pretty fascinating, right? How can you estimate something that you don't observe? So the model is about potential clients being given congestion information, and based on that, they decide to join or bulk. But the bulking clients are not observed. Still, you want to know how many of them bulk, right? So that is useful because you want to know how much supply you have missed. Well, then, like a cliffhanger for Liron's talk after my talk, we are actually able to estimate the load corresponding to clients who don't join. Well, that sounds impossible at first glance, but you can actually do it. And Liron is going to tell you how. Well, the other project with Liron that I would like to mention is this one, in which we consider like an MG1, and we want to say at what point in time we are statistically certain that the input has changed. So that is based on the workload. And there we work with so-called quasi-busy periods to create some independence. I think it's a very interesting concept, and I think it has the potential to be generalized to more, well, broad settings. Conclusions regarding this branch, I think existing queuing results can be used to construct estimators. So there's a lot of queuing knowledge that can be exploited there. The main objective is, I guess, to come up with estimators with certain performance guarantees, consistency, asymptotic normality. In my view, well, the analysis is still pretty much case by case, so there's really lack of an overarching theory. So there have been a few papers with more broader perspectives, very nice papers, I think, but still, well, a lot of progress can be made there, I think. Okay, so let's move on to the third branch. And the third branch is about techniques in which we deal with parameter uncertainty. So to sketch what the problem is, let me tell you a bit about a paper that I came across like 25 years ago, perhaps, paper by Grosklauser and Say about measurement-based admission control. What is the problem there? Well, basically, the problem is that you have a resource that is used by a couple of flows. A new flow is arriving and you wonder whether it can be admitted without violating a certain quality of service constraint. In this setting, you measure parameters or you estimate parameters, which of course differ from the true ones. And well, the question is how to deal with that. Second complication, I'm not going to say much about that, is that the load also fluctuates over time. I'm not going to say much about that. So what is the question here? Well, you have to decide whether a new traffic flow can join the system given a certain performance target, and that could be like the loss probability P. So you have to make the decision based on the current estimation of your loads, and perhaps it's versioniness or so. And what people typically do is that they use the so-called certainty equivalent method, and that is that you do as if the estimated load is the correct true one. Of course, you make a mistake there. You're too optimistic because there's also the uncertainty of your estimates. And then there's that wonderful result that Grosklauser and Say prove in their context. If you do if you follow the certainty equivalent method, but you don't use the target probability P, but P squared, then everything is fine again. So then you have covered the uncertainty of your estimation in the correct manner. Well, that's of course in the context of their model, and of course there are some conditions and stuff, but it gives a very nice perspective on how to think about this problem. So this is a paper that inspired me a lot, and I liked very much reading that. One of the spin-offs, I think in a very indirect way of that paper, was this project that I did last year with a student of mine, with Rens Kamphuis. It's about, well, how to deal with parameter uncertainty in routing for road traffic. How should you do that? Well, I guess the classical way is that you say, every per edge travel time has a certain mean, and I put those mean into the Dijkstra algorithm, and that gives me like the best route from a source to a destination, right? That's an easy way to get it done. But then you, of course, you neglect the variability of the travel times, and that is relevant to the user, right? There are situations in which she can choose between a route with a small mean and big variance and one the other way around, and then it's up to the user which one she would prefer. So there is this notion of risk aversion that you have to take into account. But also, I think it's relevant to include the estimation error. So there could be a route in which you have like a low variance of your travel time, but poorly estimated, and the person who is going to make the decision or has to choose between multiple routes could take that into account. And we sketch here a framework that, well, basically tells you how to deal with this choice problem. An entirely different approach is this robust approach. So there you think about this parameter uncertainty issue in a radically different way. So you work with uncertainty sets that are satisfied by the arrival in the service processes. And then, well, the construction of those uncertainty sets can rely on data, for instance, confidence intervals based on a CLT approximation. And from that point on, it becomes like an optimization problem. So you can use like robust optimization to get like the worst case bounds on the performance, the queuing performance of that system. Right. So this is a radically different approach, and I think very interesting and also very successful. So this paper by Bandit, Bertsimas, and Youssef is, I think, a great read to get introduced in that area. A paper that I know a bit better is about more or less the same topic, but then in the context of appointment scheduling. Well, they basically did the same, these three authors, Mak, Rom, and Zhang, a similar approach. And one of the spin-offs of their study was that in terms of the appointment scheduling problem, it's actually optimal to start your schedule with the client with the highest with the lowest variance, and then, well, order them in an increasing order of variance. And if you think a little bit about it, that actually makes sense. Some conclusions regarding the parameter uncertainty parts. In the first place, there are methods that somehow quantify the estimation uncertainty and incorporate that into the decision making. So the MBEC paper is an example of that. The second approach works with these uncertainty sets, and then, well, it pretty much becomes an optimization problem in which you can work your way towards worst case bounds. And I think they complement each other very, very nicely. Well, so these were three of the 5 branches. Number 5 is about techniques that jointly estimate and optimize. So I already said something about that before. So there's this paradigm that says, well, there are situations in which you want to learn from the system, but at the same time, you want to use the information that you get out of the system to already optimize, right? So you'll simultaneously do that. And what is the basic framework to think about this type of problems? Well, that is the multi-arm bandit, and probably many of you will know this framework. I'll briefly sketch it. So you have K arms, you have capital T rounds. Every arm has a certain reward, RK, with a certain mean, and the objective is to detect the arm with the highest reward. So a very natural framework. So when you pull an arm, well, you get information about, well, that's the random variable underlying that. In every round, you choose a specific one. So in round T, you choose K of T. Well, that leads you to a reward. And in round T, only the R of T is observed, meaning that the choice you are making in round T has to be based on, well, the previous outcomes R1 up to RT minus 1. So what is it that you would like to minimize? Well, that is the regret, which is your optimal value. Remember, mu star was corresponding to the best arm. And you have to subtract, well, what you got out of it because of your strategy. You want to minimize this regret. Well, in many settings, you can do that exactly. And then the goal becomes, well, find the growth rate of R of T corresponding to a certain strategy that you think is sort of, well, optimal or good or whatever, and prove that no alternative strategy is performing better in terms of this growth rate. So that is, well, basically the question that you come across in many papers on multi-arm bandits in all kinds of contexts. So one important point in the context of this standard multi-arm bandit problem is that, well, there's independence between all the arms that you pull. So one very nice paper in the queuing context, bandits in the queuing context, is this one. So it's written by Krishnasamy, Sen Johari, and Shakotai. Well, basically, it's a very similar context as the standard bandit problem, but now, well, the arms correspond to queues. What do they want to do? Well, basically, they have a queuing system with multiple servers, each having a specific probability of successful service, but we don't know this probability. And we want to go for, well, finding the best queue. And that is, of course, very similar to the multi-armed bandit problem. So the way they approach is that they want to minimize the expected queue regret. So the difference between the queue lengths obtained by the algorithm and the optimal value. And as it turns out, I'm not going to go into details. There is pretty delicate behavior that you have to deal with, where one needs to distinguish between an early and a late stage. Very important is that the queue observations are not independent, right? So there's always memory in a queuing system. So you have to work with that. So you have to find a solution to cope with that. And that leads to all kinds of crucial differences with the standard multi-armed bandit problem. And they manage to find all kinds of beautiful results. So Ramesh will talk later at the workshop. I'm not precisely sure whether he will be talking about this problem or a related problem, but yeah, it's probably going to be a very interesting talk, knowing him. A very much related problem that I came across is described in this paper by Stahlbuch, Schrader, and Modiano. So the setting that they look at is pretty similar. So there are K channels for transmission, but they have the distinguishing feature that those channels have time varying rates, and we don't know the statistics of those. And those you want to learn to optimize the regrets. And I guess one of the stunning things of this paper is that they managed to come up with an algorithm that achieves an extremely low regrets, namely just log of t. So that's extremely low. So I liked this paper a lot. I think it's a good read. A few conclusions regarding this branch of research. I think, well, multi-armed bandits and regrets are very useful concepts also in our queuing setting. So we want to use those concepts when we want to, well, talk about these problems. I think there's a very fruitful interaction with researchers from theoretical computer science and also from information theory. And I think there are, well, many open problems that still need to be addressed. And I think, well, with our queuing background, we can really contribute here. Okay, so let's go to the last branch of the literature. And I think it's the branch that is actually closest to what I call the traditional queuing literature. So it's all about, well, devising queuing strategies that take into account the current state of the network. And of course, the objective is to reduce the congestion level or to optimally design the system. So if you want to know more about, well, this kind of questions, have a look at this book by Moore. So she wrote a wonderful textbook with lots of examples on performance modeling and design of computer systems. And, well, the themes that you see all the time are things like, can I come up with a policy that optimally assigns tasks to servers? Well, there's a lot to be said about service disciplines, smart scheduling. So there is the recent work by her and co-authors on SOAP. I think these are very interesting topics. And of course, there is, well, a data-driven aspect to it, right? Because you have to observe or measure your current congestion level. So you have to find a way to sort of summarize what the congestion level at a certain point in time is. And on top of that, well, there is this issue that, well, there can be noise in the congestion information that you observe, or there could be delay. So you have to cope with that in some way. And I think there are quite interesting questions that are open and have to be dealt with. So one paper in this area that I enjoyed reading very much was this one, I think written in 2009 or so by Adam Weirman, Lachlan Andrew, and Ao Tang. It's about speed scaling. And basically it's about a problem in which you observe a queue, or you are working with a queue, and the service speed depends on the current, well, observed buffer content. And you can imagine that, well, it makes sense to work with those strategies, for instance, to work faster when the queue is full and work less fast when the queue is relatively empty. So one of the findings of this paper is that actually extremely simple policies, a constant rate when the queue is not empty, for instance, work already surprisingly well. So they come up with all kinds of results in that direction. And one other interesting feature of this paper is that they also provide insights into, well, the effect of parameter uncertainty. So it also relates to one of the previous research branches that I have been describing. A related topic that is highly relevant, I think, in this context is well, about queuing strategies in networks. So if you have a stochastic processing network of the type that we have been working with already for decades, can we come up with like an optimal control strategy? Well, we all know that it's very hard to do that. And one of the, let's say, novel ideas is that we could try to use reinforcement learning techniques to do so, such as advanced policy gradient algorithms. So one of the recent papers in this area, and I think it's a very promising line of research, is this one by Jim Dye and Mark Lutzman. And basically, I guess the main message is that they managed to come up with an algorithm that consistently generates control policies that outperform, well, all kinds of state-of-the-art heuristics that have been developed in the literature. Well, I'm in the process of reading this paper, so bear with me, but Jim will talk about it later in this conference, so you will definitely know much more about this topic at the end of the workshop. A few conclusions regarding these congestion-based queuing problems. From my perspective, I think they're the closest to, let's say, traditional queuing. But as it comes to optimization, I think there is a huge potential of, well, teaming up with other disciplines. Machine learning is extremely promising in this context. It covers many classical problems, such as queue assignment, load balancing, rate allocation, as we did for TCP, scheduling. So we can work on these problems again, and now seen through a different lens. But in practice, the congestion indicators that you would like to use are, well, quite often noisy and delayed. So there are all kinds of questions that you have to resolve there. So there could be statistical issues as to how reliable is your congestion signal in terms of telling you something about the current load on your system. There's always delay in the feedback. Yeah, so there are all kinds of intriguing problems to be resolved there. And I think very important is also that there is a strong relation to Markov decision theory, to optimization in general. Of course, there is the relation between reinforcement learning and Markov decision theory. So I think there is ample room for research there. Okay, so this brings me to the end of my talk. So let me end up with a few very general high-level conclusions. First one being the obvious one, that this was my view on the fields. I sketched a few problems that I think are worthwhile to look at, and I well, described a few papers that, well, have been very inspiring to me. Well, I think it's fair to say that the data element sometimes leads to new queuing problems. So think of the overdispersion problems, for instance. And sometimes non-queuing techniques like bandits and machine learning can be used to help solving queuing problems. So that's also a very nice message for our community. And in the third place, of course, sometimes existing queuing theory can be used. I think a very general conclusion is that this is really a very thrilling area with a lot of scope for interesting and highly relevant work. And I think I stop here. Thank you very much.
Thank you, Michel. That was a great overview, and thanks for all the helpful pointers for the rest of the workshop. We've got a time for just a couple of questions, and you're welcome to put them in the chat, or if you put your hand up, we can give you audio. I guess we've also got our other panelists up. Michel, in one of your branches, you identified the potential of recent work in machine learning techniques, and our third speaker today is going to give us an overview of how we can use information and learning in queuing systems.
Yeah.
So a practical question from me is, how do you see the field progressing? Do you expect your postdocs to be knowledgeable about queuing and machine learning, or are we going to be working in interdisciplinary teams to address these new problems?
Yeah, so that is a question that Neil and Jim can say much more about than I do. So I haven't done that yet. My sense would be that both approaches could work, right? So you could work with somebody with a let's say an applied probability background, and then going into machine learning, really seen from our perspective, so the queuing perspective. The other approach could work as well, but so then you have somebody who's a bit more mature into like machine learning, and then you try to do things together. But that, I guess, that can be done better in a context with two more senior researchers, I think.
Mm-hmm.
So both approaches work out well, but I'm very curious to hear what Neil and Jim are going to say about this thing. It requires, of course, us to also learn more about, well, adjacent fields, and I think that's fair. Also, for them, it requires them to learn more about queuing, and yeah, let's see what the middle ground is.
Yeah, absolutely. Would anyone like to pop their hands up for a question before we take a short break? Well, I think if we take a short break, just for a few minutes before we resume the session, and we return back with our next talk, Dr. Liron Rabner.